Hello, welcome to Picture Me Coding with Erik Aker and Mike Mull. Mike, Happy New Year. This is our first episode of 2025.
Happy New Year.
Mike, this week you wanted to talk about the paper, Propositions as Types from Phil Wadler. Paper came out in 2014, and I encountered it from Wadler's Strange Loop talk in 2016. At the time, I was kind of a Haskell nerd, and I was very excited about this talk. Wadler, one of the key people who helped create Haskell and develop it to what it is now. But we are not experts in this, as in really we're not experts in many of the topics we talk about. And you actually have brought today a special guest who can help guide our discussion and help us with our confusions and our questions, I think, yeah?
That's right. Our guest today is Nathan Mull. You might notice the similarities of our last names. Total coincidence, I've never met this person before.
It's a common name, is it?
No, in fact, Nathan is the older of my two sons, but he does have some expertise in this area, so he seemed like a good person to have as a guest. Nathan, could you introduce yourself and tell people about your background and history?
Sure. Yeah. Well, hello everyone out in the podcast listening universe. Right. As I said, my name is Nathan. I, at the moment, am a lecturer teaching faculty at Boston University. But before that, I was at UChicago and I did my PhD in type theory. So in theory, I am an expert in at least part of the topics that we are going to be talking about today. Before that, I did a little bit of proof complexity, another area that has connections to logic. And, throughout my undergraduate, I was always interested in logic. So I was happy to have the time to be able to study all of this during my PhD and have a lot of fun reading about these sorts of things. I've read a lot of different perspectives on propositions as types, which we'll be talking about today. So that should be a fun thing to chat about.
It is an honor to have you here. It's kind of you to come and help us understand this paper.
As a weird coincidence, both Nathan and Erik are alumni of both Berkeley and UChicago.
So, oh, wow. Yeah. There's a correspondence there.
Yeah, it's a surprisingly large group too. Every once in a while, I'll meet another person with the same academic pedigree.
Although I don't have a PhD, so I don't think I would put myself in the same set that you're in, Nathan.
You were there. It counts.
I was cold sufficiently long enough.
Sure.
So, as you know, Nathan, this Picture Me Coding is the number one podcast in the music podcast about software space. And So we always talk about music, or we try to talk about music. Nathan, as an aside, is a fairly accomplished musician as well, and listens to a lot of music and has had influence on my musical tastes. So tell us what you're listening to these days, Nathan.
Sure. Yeah. Well, accomplished might be strong. I haven't touched many of my instruments during the semester when everything's really busy. Tends to get a little bit less time. But yeah, I thought I would talk about. I've been listening to a little bit less music this year, but there's one album that I listened to on repeat for a very long time, and it's still one that I go back to. So I thought it'd be a good one to chat about. And this is a live jazz recording by a saxophonist named Ben Wendell and a small, I believe it's a quartet or a quintet. I honestly don't remember. All of the musicians in the group are very impressive. It was a live recording at the Village Vanguard, so, a fairly well-known place for these sorts of things. Yeah, what can I say about this album? It's, right, again, every musician in the group is incredibly impressive, and it's one of these albums that, one, benefits a lot from listening with headphones, as nice of headphones that you have, and two, multiple listens. So like the first time you listen to it, or the first time I listened to it, the saxophonist will do these just insane runs. I don't understand how he can manage to have that much breath to be able to continue through these really complex runs. And maybe on the first time you might start to hear some of the back and forth play between all of the instruments. And then maybe the second time through, at least for me, I was starting to realize, oh, wait, this drummer is absolutely insane. Like, I have no idea how this drummer is, one, maintaining the beat with like his right foot. His right foot must be incredibly tired on that hi-hat, and but also just doing these fills that I have more imagination than I could possibly have with respect to percussion. And every time I come back to this album, I hear some additional feature of it that just kind of blows me away. I think there are albums that I listen to on repeat, and then I've listened to it too much, and I kind of put it aside and find the next thing. But this one, for some reason, I always find myself, another listen through this could be really nice, and so I think it's a good one to look through.
What was did you give us the name of the record? What was it called again?
Oh, the name of the record is Understory, live at the Village Vanguard, and this is Ben Wendell, the saxophonist.
Nice. Do you get to hear like tinkling of ice cubes and glasses and stuff too? Is it that kind of live jazz album, or is it? It's mic'd a little better than that.
Yeah, I think it's mic'd a little better than the Evans Trio album, also recorded there, and it's a lot more high energy than that album. So it would be kind of hard for those clinks to break through some of that high energy music.
Okay, nice. We'll have to check it out.
Yeah, no, sure.
All right, so we wanted to talk about propositions as types. I remember watching the video. It came out in 2016 it was recorded at the Strange Loop conference, and the paper had come out a couple years before that. I remember watching this video and being really excited and sending it to all my coworkers and annoying them with it. Like, see, this is why we should be using Haskell at work. The paper, as we come back to it, as we read it again to prepare for this, I remember I feel like a little less enthusiastic and more maybe critical as I read it. But there are some great lines in it. So I just want to read the first section here. Wadler writes, "Propositions as types is a notion with mystery. Why should it be the case that intuitionistic natural deduction, as developed by Gensen in the 1930s, and simply typed Lambda calculus, as developed by Church around the same time for an unrelated purpose, should be discovered 30 years later to be essentially identical? And why should it be the case that the same correspondence rises again and again?"
Yeah, to me, when I first read this paper, I confess I did not understand what it was talking about. And it's still a little bit tricky for me, but it's just it's one of those things that's either deeply profound or completely ridiculous. I'm not sure which.
Nathan, are you used to people saying this about your field? Well, it's either deeply profound or kind of pointless.
Yeah, no, I mean, that's pretty much all of academia. No, I was saying this before we started recording, but this is also something that was shared with that I shared with my advisor, that it's one of these topics that you look at it the first time and you're like, I don't understand what's going on at all, and then you start playing around with it and you're like, okay, I'm starting to see how this works a little bit, and then you look at it a little bit more and you're like, wow, this is absolutely beautiful. And you look a little bit more and it's like, wait a second, I don't understand this anymore. And then you see another thing and you're like, okay, now I'm starting to feel everything click in again, but I'm going to tread a little lightly moving forward.
I would recommend, so if you're encountering this for the first time, listening to us talk about it here, I would strongly recommend go out and try to watch the YouTube recording of the talk. And there's some good jokes in there. It's a dynamic talk. It's fun to watch. But we're going to we'll try to make a little bit of a connection to our field, software engineering here, if there is one. Mike, did you want to jump in?
Should we go through this part of the paper that talks about the Curry-Howard correspondence?
Yeah, I think so. Yeah, that makes sense. So the foundation here at the beginning is the paper is about the term proposition types seems to refer to this concept that is more generally called, and again, Nathan, jump in if I'm saying stuff that's wrong, the Curry-Howard correspondence. And Philip Wadler gives a summary of it early on. He says, at the surface, the Curry-Howard correspondence says that for every proposition in logic, there's a corresponding type in the programming language, and vice versa. Thus, we have propositions as types, logical propositions as types. And he says it goes deeper, in that for each proof of a given proposition, there's a program of the corresponding type and vice versa. Thus, we also have proofs as programs, and it goes deeper still, in that for each way to simplify a proof, there is a corresponding way to evaluate a program, and vice versa. Thus, we have simplification of proofs as evaluation of programs. So this is the core idea in the paper. What the hell does that mean?
Yeah, well, I would just jump in and start by saying proposition is types. It's a very pithy description of what's going on here. But even within the field, it's the term propositions here has a little bit of, term overloading. I think when Howard first introduced this, it was formula as types, which might not be more clear unless you are in the field of logic. But what I might say alternatively is something like mathematical statement or logical statement as types. So the idea being that we should be able to read the types in our programs as statements that you might see in a math textbook or in a logic puzzle, like such and such has such and such property. The term proposition is kind of this slightly ambiguous term in the area of mathematics and logic and philosophy.
So there's a connection between logic and mathematics and types in programs. And I guess I would, if I am reading this naively for the first time, I'm thinking, okay, does that mean if I'm writing a Java program and I've got, not the kind of type system I would have in Haskell, does this also apply to Java programs and the types in a Java programs? Are those also related to logical propositions? Is writing a Java program also a proof of something?
Yeah, no, I mean, I think that's a great question. And I don't know if we want to get into this right now or all the way at the beginning, but I think one of the first questions that particular programmers have when they encounter propositions as types for the first time is, okay, I know what an int is. Is an int a mathematical statement, or is int a mathematical statement? And it's a fair question. And it's even one of those questions that has a little bit of debate within the field as well. For all intents and purposes, it's reasonable to just say no. Int is not really a mathematical statement. On the other hand, there are people that will say, "Oh yes, int is a mathematical program, and 2 is its proof, or 10 is its proof." But that's something doesn't quite ring right when you hear that for the first time. But going to Java. If you think, for example, in the context of Java generics. So if you have a function that uses generics, let's say type T, and you have a program of type T arrow T, or a function that takes T's and gives you back T's, you can think of that type T arrow T as the statement that T implies T, or that my name is Nathan implies my name is Nathan, where T stands for any proposition that you can make in English, mathematics, logic, etc. Mm-hmm. And what's interesting is that if I asked you write a program of type T arrow T for some generic type T, you really only have one option. You take its input and then you give it back. And that's kind of exactly how you would think about proving the statement, my name is Nathan implies my name is Nathan. Well, you say, well, you told me first that my name is Nathan. I'm going to give you back that statement, and that'll be the proof that, in fact, your name is Nathan.
I was thinking as you started exactly of the identity function in Haskell. It was like a year or two before I looked at the identity function in Haskell and realized, wow, if you have a type variable A, there's nothing I can tell you about what is inhabiting that type. Like I couldn't do anything with it except give it back to you. Like I can't assert that I could turn it into a string in Haskell. I can't assert that I can build some kind of Boolean value out of it. The only thing I can do is give it back to you.
I think one thing that's slightly confusing maybe to mainstream programmers is that so if you have a function that takes an A and returns a B, I think as a normal programmer, you think of that as a function that has type B. It really has type takes an A and returns a B.
Well, I guess in a language like Java, it's been a minute since I programmed in Java. You can't write anonymous functions. Are there closures in Java? It's been a long time since I've actually programmed.
I think it does have closures now, yeah, and there are lambdas.
Yeah, so if you have lambdas and closures, and then you think about what is the type of the lambda. So I think if you're thinking about types in this way, it's easiest to imagine, you're in this restricted setting where you're not allowed to take any parameters in any named function. You always have to name a variable and then assign it to a closure. And then the closure tells you the type of the thing that you care about. So if you have the closure, which takes an argument and then gives you back something.
We're getting a bit off track, but what you just said sounds very lambda calculus to me.
It is. I mean, in a sense, it's yeah, exactly that. I also wanted to just point out that this whole idea that the only kind of function, or there's only one option of a function that you can write, which is the identity function, was something that was observed and generalized by Philip Wadler in his paper Theorems for Free. And it's this notion called parametricity. And there are lots of other examples in the context of polymorphism of functions that have exactly one or exactly two possible implementations. Just a side note.
It was kind of surprising to me once once it like clicked that was the only possible program that you could actually write that satisfies this type signature. It was like light bulb.
Yeah.
So what about the sometimes the comparison of a type to a set? If I talk about the type of natural numbers, or I talk about the type of strings, we can sort of think of those as a mathematical set potentially, right?
Yeah, in a way. And I think that, and we had a bit of a discussion about this offline, but I think when you're first approaching these ideas, that's a very reasonable way to look at it. Especially because for very simple type theories, you can in fact formalize that and say, yes, in fact, we can imagine the meaning of this type as being a set. There's this kind of unfortunate feature when in expositions about type theory that there's this very early chapter which says this is why types aren't sets. And when you're first learning, it's very hard to motivate that. But it doesn't take too much more complication for sets to no longer be a good analogy for types.
Okay.
But at the beginning, I think it's a very reasonable place to start.
Okay. All right.
Yeah.
So one other question I had for you here at the beginning is Wadler talks about the Curry-Howard correspondence, but then he has a phrase in here where he says, and this sounds almost argumentative, like he's having an argument with people who I don't know who he's talking to. And I kind of have heard vague rumblings of this. He says, again, logical propositions as types, proofs as programs, simplification of proofs as evaluation of programs. And then he has this kind of dense sentence for me. Hence, we have not merely a shallow bijection between propositions and types, but a true isomorphism, preserving the deep structure of proofs and programs, simplification and evaluation. And this gets to something I've heard people say, and I maybe I'm overstating it. I just sort of heard almost rumors of this. Is it a Curry-Howard correspondence or a Curry-Howard isomorphism? Do people disagree about how strong the connection from propositions and types is? Is there some sort of argument happening here that we don't know about?
Yeah, the secret deep state argument about what does propositions as types actually mean? No, I mean, I think it's a great question. I will say, I don't know how far we want to get into this right at the beginning, but the short answer I would say is yes, it is a fairly deep isomorphism in the formal sense. And in fact, calling back to UChicago, there is a professor in the philosophy department at UChicago named Kevin Davey, who's writing a textbook at the moment on type theory for philosophers. And he only has a couple chapters on his website at the moment, but he sent me a draft of it when I was still at UChicago, and he takes this very explicit approach about the isomorphism. Like, here is a logic, here is a type theory, and here is a literal function that maps between the two that preserves some notion of structure that I've defined. So the point is, if you wanted to, you could make it as formal as you wanted as a notion of isomorphism that is, mathematically reasonable to anyone who cares about that kind of like algebraic notion of isomorphism.
Okay. All right. So you've won me over. I just didn't know if I say, oh, the Curry-Howard isomorphism, are people going to go, no, you're wrong. That's just a correspondence. Well, I think you've satisfied my question of I'm not saying the wrong thing.
You're not saying the wrong thing. I think it's just there are some people who will say, oh, well, I don't actually want to think about this as a isomorphism, because in the same way, we've already said, int doesn't seem like a natural mathematical statement. So I don't want to commit myself to saying that 10 as a proof of the statement int. I would rather have a separation between what I consider the logical part of the types that I care about and the computational part of the types that I care about. And that's why in certain proof systems or proof assistants like Kak or Agda, or I guess it's now Rock, there is a distinction between these two things. There is the part of the type system which deals with the math, and then there's the part of the type system which deals with the computation. So in Lean, for example, int is not a mathematical statement. It is a distinct thing from a type which represents a mathematical statement.
Oh, okay. Do you, when we start talking about this paper, do you think that there are, again, our audience is mostly software engineers probably, do you think that there are programming languages that are more likely to be like, and maybe not analogies for, but like that where you can take these ideas and see them a little more plainly? A language like Haskell probably, but does a language like Rust count? Do these things apply to all languages, Java, C, whatever? Or is it easier if we use specific programming languages to say, here's where these ideas emerge?
Sure, yeah. So I think seeing it in practice is probably the most important thing of understanding this idea, because until I started actually programming, like writing the programs literally by typing them, I didn't really understand the correspondence. That said, it needs to be a programming language that's strongly typed, so it needs to have a type system. It's useful to have anonymous functions, so something like lambdas, something like closures. And really, that's all you need to start to see the rudiments, because the point is that once you have, in essence, a copy of the simply typed lambda calculus, which is just a strongly typed collection of anonymous functions, you can start looking at the types of those programs that you can write in that way and seeing if you can reason about them as mathematical theorems. I know this might be preempting it a little bit, but even just like, one step further than the identity function, if you think about the function composition function, something that takes a function from A to B and a function from B to C, and then gives you back a function from A to C, that's also something that you can read as a mathematical statement, that if A implies B and B implies C, then A implies C. If it's raining, then I'm wet. If I'm wet, then I don't know, my shirt is soaked. Therefore, if it's raining, my shirt is soaked. And if you think about what kind of program you can write that way, it's pretty much only one possible program that you can write. And it's the kind of program that composes the two functions, or basically says, take your first implication, look at its output, pass that into the second implication, look at its output, and that's your conclusion. But yeah, so it's a fun game to play. Like once you start something like Haskell, something like OCaml, something like Java with closures, just looking at the types and seeing if you can read them as a statement.
So we've mentioned lambda calculus a couple of times already. In the very first part of the paper, Wadler talks about church and the lambda calculus. And I think in this introductory part, he's mostly talking about what he calls effective calculability, the famous what's the word German word again, Erik? You pronounce it better than I do.
Problem. Yeah, so this goes back to the foundations of our whole field, right? You've got Turing and Turing machines. You've got Alonzo Church. They're hanging out at Princeton together. You've got Kurt Gödel. You've got Hilbert's plan. Are computations decidable? We need a theory of computation to be able to produce an answer. And you've got Church's lambda calculus and Alan Turing's Turing machines, and Turing's paper is this proof that these things may be decidable, but we can't prove them. I may be doing a really bad job. Put on the spot there. Close enough. So he talks about decidability here at the beginning. Sorry, he talks about theory of computation here at the beginning and lambda calculus. I took that away from you, Mike. Where were you going with that?
I just basically want to get a sense of, is this effective calculability idea essential to propositions as types? Is it just saying that, we needed something that gave us a theory of computation?
Well, I will say the first time I read through this, it took me a second to realize just expositionally what Wadler was doing here. My understanding he begins the paper with this idea, how could it be the case that this lambda calculus, and this other thing, this proof theory by Gensen, could somehow be really doing the same thing. And so I really think the primary purpose of this first section, I could be wrong, but my understanding is that it's just to say, okay, here is this completely different vein of academic research where people are thinking about computation and effective calculability. And from that, we get the lambda calculus, and in particular, the simply typed lambda calculus as a way to fix, quote unquote, fix some of the issues of decidability with the untyped lambda calculus. But I mean, in the same way that maybe you're hinting at here, I was a little bit confused about the role of this first section, besides it just being a collection of very interesting facts in the history of the theory of computation.
There's a really good joke in here, and I don't really want to ruin it. Maybe I'll ruin it anyway. If you watch the talk, the joke is delivered pretty well, but he says, you have this concept of an algorithm that shows up in the 1400s, maybe, Al-Khwarizmi, and then you wait around 600 years and you get 3 theories of computability. And so it's like waiting for buses. You wait for hours and then all of a sudden 3 show up at the same time. I'm ruining his joke. But then he starts talking about the halting problem. He's saying that if you got simply typed lambda calculus, if you have general recursion, it's effective computability. Maybe I'm using that wrong, but like you can compute anything, right? When we say it's Turing complete, you can compute whatever any computer program can compute. And he says, well, that's cool, but if you remove your general recursive, then you have no halting problem, right? You can't compute everything, but you could be sure that every program you ever write terminates. And I was like, well, that sounds cool. And then I went, but wait a minute. I write in programming languages every day that have the halting problem. I could end up looping forever, right? Like, do I care about this? I don't know if I care about this early on.
Yeah, no, I mean, I think that's a great point. And I think particularly when you first see it for the simply typed lambda calculus, this idea that every single program you write in the simply typed lambda calculus halts, it's not immediately clear what you're supposed to take from that. On the one hand, it's like, okay, great. That means that I have one fewer thing I ever need to worry about. The other thing is, well, if I told you, okay, you can program in Java, but you can only use anonymous functions and variables, and that's it.
No looping.
You'd
right?
be like, well,
no looping concepts.
Yeah, no looping. Yeah, it's like okay, I can't do anything here. And this is why there's no programming language out there that's built strictly out of the simply typed lambda calculus. It's just not powerful enough to do anything that we actually care about doing.
You mentioned Gensen briefly. I'd never heard of him, but you kind of mentioned offline that he's pretty prominent in mathematical logic. Could you give us just sort of a brief idea of what he did and why he's well known?
Sure. Yeah. Well, I will say I'm not a proof theorist exactly, so I won't get this exactly right. But people tend to think of Gensen as the father of modern proof theory. So what Gensen did, his main contributions were two, at least, he might have had more, but at least 2 formalisms for saying what exactly a proof is. So before proof theory was a theory, we had this notion of proof that everyone used when they wrote down proofs for mathematical theorems, but not that many people had sat down and said, okay, well, if I want to think about a proof as a mathematical object in its own right, then what does that have to look like? And so it's mentioned in the paper, but the 2 systems that he created are called natural deduction and the sequent calculus. They are fairly different, but they each have their own benefits. Outside of that, once he had those 2 systems, he proved some very interesting things about these systems, sort of initiating this view of proofs as objects that I can manipulate, that I can apply mathematical arguments to. And the one that is, or the result that is most pertinent to this paper, is this notion of proof simplification, or in other words, this idea of eliminating redundant arguments or unnecessary arguments in proofs.
Is it fair to say that without Gensen, it would have been difficult to make this propositions as types correspondence?
I think we would have made the propositions as types correspondence, but the idea of the deep isomorphism, the idea that in fact the notion of proof simplification that Gensen gives, and maybe at some point we can give a slightly more exposition on what exactly that simplification is. But the idea that that notion of simplification actually corresponds exactly with what we call computation in functional languages like the Lambda calculus, that I think wouldn't have been so clear and wouldn't have been quite as exciting if that wasn't there.
So maybe proofs were a little fuzzy, is what you're saying, before Gensen came along. He formalized the notion of...
I mean, there were people before him, like Frege had a fairly formal notion of proof when he was formalizing arithmetic, and Frege was also piggybacking on some earlier names who, at the moment, I don't remember. So there were inklings of notions of formal proof in the world of modern logic and whatever that is. But I think it was really... Gensen, who one came up with the formalisms that we still use today, the ones that still appear in type theory and logic papers and textbooks. And two, I think the big idea is, well, what if we treat a proof as a thing that I can actually work on, not just like a thing that I've written down that's static, but a thing that I can actually like pass into like a function, like a mathematical function or a program.
All right, so the real core part of the paper is describing propositions as types, really the middle. He sets it up here at the beginning. He talks about a little bit of computation, computability. He talks about Gensen, and he says, okay, now that we have these things, we can actually describe what this correspondence really means. And I think this is one of those things where we kind of want to draw some symbols on a piece of paper or a whiteboard to really communicate it. So we'll give it a shot here. What do you say, Mike?
Yeah, this is a little bit visual, unfortunately.
Being a former Haskell nerd, it's helpful to think in terms of Haskell type signatures. At Haskell, they use the arrow to denote going from an input or an argument to a function to the output or result type of a function. So you might say int, arrow, bool in Haskell. And what you're saying is I'm going to write a function. I'm going to produce a function that will take an int and produce a Boolean value. So a arrow b means I'm taking in an a and I'm producing a b. Wadler writes, in 1934, Curry observed a curious fact. Every type of a function a to b could be read as a proposition a implies b. And under this reading, the type of any given function would always correspond to a provable proposition. Conversely, for every provable proposition, there was a function with a corresponding type. And so this is what he said above. You write this type signature if you can produce a program that satisfies the type signature that's well typed. The program itself is a proof that the type is valid, that the proposition is true. Is that right? Did I overstate it?
No, that's exactly right.
He says we could describe Howard's observation as follows. Conjunction A and B, these are logical operators, right? Logical connectives, A and B, a proof of A and a proof of B. And he says this corresponds to the Cartesian product, A, B, like a pair, a tuple of A and B. So a proposition of A and B consists of a proof of A and a proof of B. And if you can produce a value of A comma B, that's similarly a proof of A and B. If you have A or B, that's the disjoint sum. This is super common nowadays. Algebraic data types, enums, people using Rust who are pattern matching on their enums or Haskell pattern matching. They're dealing with sum types. I either have this or I have that. A proof of A or B consists of either a proof of A or a proof of B, including an indication of which of the two has been proved. And if you have a value of A plus B, it's either A or B, including whether it's the left or right summand. So it's like, again, if you can write a program that takes a sum type, an enum, an algebraic data type, and that program is well typed, you've proved that proposition A or B. And finally, implication, A implies B, corresponds to the function space, A arrow B, A to B, a function that takes an A and produces a B. So value of type A to B consists of a function that when applied to A returns the value B. Now, this sounds pretty cool, but I guess I sometimes get a little bit, it sounds cool, and then I go, well, wait a minute, do I care about what does implication mean to me? I really want to put some values into my program and get some values back out. And somehow if I can write that program, I've proved that it's possible to do so. But I'm sort of begging the question, yeah, as a working programmer, I'm sort of getting myself lost here. Mike, save me.
Well, I guess, one question I would have is that from a practical perspective, I know Nathan has talked about how these ideas have influenced the development of programming language theory and design. So there's a connection there. But I guess my question would be, as a programmer, do I ever really need to think about the fact that my function is a proof of something? Or is it only the inverse thing, which is interesting, where if I'm a mathematician, I can write a program to do a proof?
Yeah, well, my personal take here is that when it comes to everyday programming, this doesn't matter. it's a very neat connection. It's very cool. But hey, the other thing that's really important to recognize here is that all that the correspondence says is that if it is possible to write a program for a given type, then you've proved the proposition corresponding to that type. The thing is, when it comes to programming, you don't care about writing any program. You care about writing a good program. You care about writing a fast program. And this correspondence is completely ambivalent to what kind of program that you write to prove the corresponding proposition. So the only time that it should really matter to the everyday programmer, this correspondence, is if you really want to be reading your types as statements. So, I mean, one example that I give of why this might matter to programmers in the future, this is completely, forward-looking. I have no idea whether or not this is a reasonable statement at all. But we might have a chance while we're here to talk about dependent types. And the point is, the rough idea is basically that if you create a slightly stronger type system than most languages, there are some languages that have this, you can start expressing more complex things. And in particular, you can start expressing reflexive statements about the program that you're writing within the program itself. So I can say, rather than saying that a sorting function is a function which takes a list and then gives me back a list, I can write a sorting function which takes a list and gives me back a sorted list. I can express the notion of sortedness in the type itself. The reason why I think that is something that people might want to care about in the future is that if we ever do get to the point that we are generating a lot more code than we are actually writing it via AI systems or whatever you want to think about in the far distant future, if we start automatically generating large pieces of code, we're definitely going to need to have some stop gates that say, that really big piece of code that I just automatically generated isn't gibberish. And to me, one of the easiest ways that I can imagine doing that is by expressing within the type itself a statement which says that the only kinds of programs that you can write are ones that have the right properties. So I guess another way to think about it is that, at least generally thinking about type systems, is that a type can restrict the kinds of programs that you can write. Like you can't write a function that has type A times B because a proof of an implication is not a proof of a conjunction. I can't write a function that throws away all the elements of the list if it's a sorting function, because what I need to get back out is a sorted function. So as far as what a programmer might care about in these concepts, it's the more general idea that types allow you to restrict the kinds of programs that you can write, which could, in theory, tell you something about how to automatically generate programs that have the properties that you want them to have.
I mean, I find that kind of line of thinking pretty inspiring. That's what drew me to Haskell in the first place. The popular notion is often phrased as making illegal states unrepresentable in code. Right. If I have a type signature in a Haskell program or a Rust program, that is explicit enough about the goals and intentions that I had for that program, my hope is that someone won't be able to come along and break it in the future because their program simply won't compile. They won't be able to write a function that satisfies that type signature. And there's something kind of exciting about that. If my types are explicit enough about things I want to simulate from the world, if they're concrete and rigorous, I guess is the word that I want. If they're rigorous enough, then I can build a computation that I'm really, really satisfied with. Now, you mentioned dependent types, and I guess the question is, do we need dependent types to get there? In the paper, Wadler says Howard proposes predicate quantifiers for all, and these are existential quantifiers, universal and existential quantifiers, corresponds to new types that we call independent types. If you've ever seen these, it's an upside down A for all and a backwards E, which is often there exists. If you've ever seen TLA plus, these show up in TLA plus. There exists an element of a set such that blah, 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 or for every element of this set, blah, blah, blah. That's what we're talking about here. And those are somehow connected to dependent types. Is that right, Nathan? Are these connected to dependent types, the quantifiers?
Yeah, absolutely. Dependent types are exactly the types that you add to a type system if you want to be able to express quantifiers. So you add a product type to express conjunctions, a function type to just express implications. You add dependent products to introduce universal quantifiers and dependent sums to introduce existential quantifiers.
But a lot of these topics get a little confused in my head. Again, I come at it from, I was really interested in Haskell for a long time, and being interested in Haskell, I got introduced to category theory, and I dipped my toe in category theory far enough to understand, whoa, I don't really understand this. And also, does this help me? I'm not sure if it helps me. Sometimes it helps me, and most of the time it confuses me. So anyway, a lot of these topics get a little confused in my head, right? I've got set theory, I've got logic, I've got category theory, and then I go over to TLA plus, and I've got these another kind of logic. I've got the quantifiers of for alls. I remembered that there was lambda calculus and then simply type lambda calculus. And then there was system F, which added a universal quantifier. And then from system F, we got, I think, and maybe I'm truncating a little bit, but then Miranda was inspired by that. And Miranda was the proprietary language that the creators of Haskell were like, well, we're going to have to pay to use this language. Let's make Haskell. So there's this kind of evolution of languages. And now there are languages like Agda, Idris, where they're like, well, Haskell's great and all, but we also need dependent types to be able to express the types of computations that you're describing, to have like a complete logic, a complete proof system in our programming language. I meant to have a question there, and I just drove the train off the cliff.
Oh no, it's perfect. I think one thing I can fill in a little bit of that storyline that you just described.
Yes, yes.
The one thing that I would, or the one addition that I would make there is that when we get from the simply typed lambda calculus to system F, or in other words, the second order lambda calculus, we add universal quantification, but it's a particular kind of universal quantification. It's universal quantification over types. So this is this notion of polymorphism. Polymorphism says, I don't just want a function from type int to int. I want, for all types A function from type A to type A.
Okay.
So system F gives you quantification over types. So the story from there then goes to a system called F omega, which I won't get into the details there, but it basically allows you to introduce type constructors. So things like lists. List is a type constructor, which takes a type and then gives you another type. Mm-hmm. And then that's the inspiration for Miranda and Haskell. And I believe, I think OCaml is actually more Hindley-Milner. I mean, there's some Hindley-Milner in Haskell as well. But right. So the idea is that once we have, that is actually another kind of quantification. And then finally, there's one last kind of quantification that corresponds to dependent types. And that's where you can start to quantify over values themselves. So not just over types, but over like ints, over strings, over actual values in your program. And so this is where things get real weird, because now computation is now playing a role inside of the types themselves, which feels like you're kind of breaking the rules, because you're supposed to think of types as these static things that never change, and the and your program. But now there's numbers in there, there's addition signs in there potentially.
I wonder if we could give an analogy to maybe Rust or Haskell. Haskell, when you write a Haskell program, you've got your type signatures, and then when that program gets compiled, those types effectively get thrown away. You end up with this computation that's just a bunch of closures, really. And dependent types is actually something different, right? Like the value that you're working with can determine the type. So there's kind of like almost a backwards looking, maybe that's the wrong way to phrase it, but the term
No, I mean, that's exactly
determines
right.
a type.
Yeah. So you can't throw away all types when you're evaluating a dependently typed program, or when you're type checking and evaluate a dependently typed program, because all those values could be useful.
I think almost everybody playing with Haskell at some point wants to write a program where they're like, well, if I get this type of value that I want to, if I get this value or this category of value, maybe I'm trying to evade the word use type, then I want to produce this result type. Otherwise, I want to produce it. And you can't write that program in Haskell. I mean, you could encode it in a sum type, an algebraic data type, in enum or something like that. There is gadgets, which I do not want to talk about right here. But in general, you can't write that program. You need dependent types to write that program, I think.
I would even point out that Rust has kind of baby dependent types, even just at the level of arrays. So when you write down an array type in Rust, you have to specify the length of the array.
Mm-hmm.
And that length is a number, or it's a U size. But that's a value in the program. So that type actually depends on a value that you can write somewhere in your program. Now, there are restrictions on, you can't, that value that you have somewhere in your Rust program can't change at runtime. You have to be able to determine it at compile time. But it almost has this flavor of baby dependent types, because you have a type that actually depends on a value that you might have written somewhere else, or a constant that you might have written somewhere else in your program.
Or const generics, I think, is what you're talking about too in Rust, where you can have a generic argument that may be like a U size that you pass in as a type. And maybe I'm restating what you're saying. Sorry.
No. I mean, I think that's slightly different, but similar.
Baby dependent types. So as Wadler continues on in the paper, he talks about intuitionistic logic. He then says, here's what's interesting about this. If we can tie logic to types and programs, well, what we can do is we can go and mine the world of logic for interesting ways to build computations in a way, right? So you might have temporal logic, and you might write a type system based on temporal logic, and you're just sort of translating it. Or you might have modal logic, and Wadler famously added monads, maybe famously in the Haskell world, but added monads to Haskell, and he was using modal logic in order to implement that. He talks about second order logics, which he relates to Hindley-Milner type inference or generic types in Java. There's some others that I don't quite follow that he connects as well. Category theory, quantum mechanics. I have no idea how those are related.
I mean, we might as well add, because we were just talking about it, Rust is entirely influenced by linear types, or linear logic. So linear logic created by Girard in the 80s. You turn that into a type system, you basically get Rust, modulo, not exactly, but close enough.
Mm-hmm. And they were actually working on implementing linear typing in Haskell. And in linear typing, I had thought in Haskell was going to be pretty stricter than, I have heard Rust called them affine types. I don't really know what that means. It's like a lighter way, like I can reuse an immutable value, but in Haskell with linear types, they were going to make it so if I express a linear typed function, what it says is, you can only use this as an input one time. I might be stating that wrong, but it was something like that. Like you were exhausting this thing. As soon as you turn A into B, A is gone. Poof. And that was the linear typing they were doing in Haskell. Does that sound? I don't know if that sounds.
I think that sounds right. I mean, I admit this is a semi-new area for me. My research wasn't in linear types, but I've been spending more time thinking about them recently. I believe that's correct. I also believe that Rust is an affine type system insofar as they kind of enforce linear typing in the basic constructs, but they do allow some contracts that break exact linearity.
But maybe you could help us though. Like, is it interesting to be able to look at the world of logic and go, wow, that hasn't been built yet? Or is it interesting to be, if you were a logician, to look at what's going on in programming languages and type systems and go, oh, wow, does this happen? People are they're looking at these other fields in order to steal ideas they can write papers about.
Oh, absolutely. And I mean, and you just gave a bunch of examples of one direction. So taking ideas from logic, using that to define programming languages. So that's a very nice example. One very interesting example, which I will not go into too much detail on, but one of the connections that we haven't talked about, it's only touched very briefly here, but I think is a very important picture in this sort of triptych that we have here is the connection to category theory. So there's very strong connections between the quote unquote semantics of a type system and category theory, to the extent that there is this notion of the internal language of a category, which basically says, I don't know how much category theory you did where you had to like show that two things were equal by using a universal property. It's this kind of long process of saying, okay, I want to show that these two things are equal, and I have to use all these facts that I know about my category. If you can show that your category has an internal language, that internal language is a type system where if I want to show that two things are equal, I just need to show that two programs of the same type are equal. So there's this kind of interesting game that category theorists are playing where they're writing programs to do proofs about the categories that they care about, because it turns out to be a lot simpler than actually doing it by hand. So like so category theorists are actually using these ideas to make proofs about equality of objects in the type a little bit easier, writing little programs to do that.
Can you give us a little bit of a sense of, this is kind of a dumb question, but how big is this world? How many people are doing this work, and what is it composed of? You got people in math departments. Maybe there are people in philosophy departments still doing logic. When I think of philosophy departments, I tend not to think of logic, probably naively, but you've got philosophy departments and logic. You've got mathematics departments, category theory, logic. You've got computer science departments. Is this a big academic universe of people, or is it very niche? Can you kind of give us a sense?
I wish it was bigger. No, it's not. It's not a terribly large field. I will say that there was a bit of an insurgence with I don't know if we'll talk about it today, but with the homotopy type theory in the 2010s, when that started to become a bigger deal. A lot of people started, particularly mathematicians, started jumping onto the type theory train to see, maybe we can get this new foundations that'll be very powerful for doing more interesting things in category theory or such algebra and such things. But yeah, I mean, even within the computer science departments, people doing PL is niche, and within the PL, people doing type theory is niche.
Okay.
If you go to Europe, there's a lot more people doing type theory and logic, like INRIA and various other places in France. And I guess what I would say is you don't need that large of an academic community for it to be very active. So it's not a very big group, but it's constantly producing stuff. So,
okay, so pretty actively, a lot of active research right now, a lot of papers published, a lot to kind of to keep up with every year.
Yeah, it's not the same as keeping up with like artificial intelligence or even graphics that have these really big venues that people are publishing to.
Mm-hmm.
But, there are, probably 20, 30 workshops every year on various topics in type theory, be it homotopy type theory, general type theory, all the fancy types like linear types, session types. And yeah, there's always groups of people thinking about these things. It's not a massive community, but I don't want it to make it sound like it's everyone is working on these super important problems. But, I guess part of the job of any academic is to convince people that what they're doing is kind of interesting.
There is a phenomenon when you start surfing, you read these surf reports, and then over time you sort of become like a hobbyist meteorologist. And of course, as a hobbyist, you're terrible at it. But like every surfer who's been doing it long enough is kind of like a crappy meteorologist. And it's similar to the people who are doing Haskell. Some of them are good at it; they know what they're doing. But a lot of us who got interested in Haskell became very crappy, like conversantly crappy at talking a little bit about category theory. But we really, like in my own case, I don't have a clue what I'm talking about.
Yeah, but I mean, the one thing about smaller communities is if you say to someone, "Oh, I'd like to talk to you about type theory," they'd be like, "Oh, of course. I mean, I love to talk about this." There's no one here to talk. There's no one here to talk about it. So,
Kind of like to just talk about this last section and see if we can sort of convey in words this idea of one thing being a proof and another thing being a program, and how they are equivalent. Unfortunately, it's also both the proof and the program are kind of written in a very visual way that's hard to convey in words. But basically, what he does in the last couple of sections is he introduces a proof in this formalism that Gensen built. He essentially wants to prove that B and A implies A and B, which, as he states in the paper, is kind of something that seems like it's trivially obvious, but sort of gives us a basis for making a comparison to the so-called program. And so then he provides the identical thing in essentially type lambda calculus. So he sort of demonstrates how you could use lambda calculus to do a computation where you go from a program that takes something in B cross A and produces something in A cross B, and voila, these things are equivalent. And
Well,
I confess,
instead of the cross, I would say even like a dumber expression of it, I would say takes a tuple of type B comma A and produces a tuple of type A comma B.
Yeah, exactly. I don't know if there's a more general way to say that, but I confess that I talked to Nathan a little bit about this yesterday, and I still am not entirely convinced how I can explain why a function from one tuple to another tuple constitutes a proof. And so maybe we can discuss that and elaborate on it a little bit.
He talks about intuitionist deduction from Gensen, and he gives this example of elimination and introduction, and then he translates it into the simply type lambda calculus program that you mentioned. And I confess, when I read this part of the paper, I'm like, yeah, I believe you. and it also seems trivially true. If you give me a tuple of B comma A, and you say, hey, give me a program, a computation that will produce from this tuple A comma B, I'm like, okay, done. Like I don't. And then if you tell me, well, what you just wrote, because you were able to produce a computation that was well typed, you've proved the implication that B and A implies A and B. There's like a little bit of the magic and mysteries kind of lost on me because the computation's so trivial. I don't know. How are we doing on this one, Nathan? Are we?
No, I mean,
we're missing it. I think
it's fair. It's also, I think there are two things to speak to. One is like, yes, it does make sense that for really trivial things, it's hard to really see the beauty in it. I mean, you kind of have to see some of these insanely long proofs of these very intricate mathematical theorems to be like, oh wow, you really did something there. Like that was an impressive program, and you proved something very impressive. I'll give that to you. And because we talked about this a little bit before we started recording, I did think a little bit about how I would try to describe to someone without any pictures what's going on in this propositions as types framework. And what I kind of came up with was, when you write down a program of a given type, there is a program in the background called a type checker that checks whether or not the program that you wrote actually had the given type. Now, sort of dropping all of the formalisms of Gensen's proof theory, it's all very beautiful, but not necessary for the analogy, which is basically, we think of a proof as just a sequence of sentences that say, okay, this is the next thing I need to prove, and this is how I prove that, and so on and so forth. So my point is that if you were to take a type checker for the simply type lambda calculus, and you put in little print statements every time before you go to check a particular kind of thing, like a cross product, you say, I'm now going to check this cross product. Then what you would get by type checking a program is a big sequence of sentences, which begins to look kind of like a proof. Now, if you were to replace all those sentences with something like, rather than, okay, I'm about to check a cross product, that this is in fact A times B, if I instead wrote the sentence, I am now going to prove to you that A and B holds, then that program or that sequence of sentences that you produce in the type checker kind of looks like a proof of the same corresponding proposition. So I think maybe the thing that's not immediately clear from this nice picture that's in the paper, and for those listening, I do recommend looking at the picture because it's very striking how similar these two things are. The thing that kind of gets lost in the picture is that where the correspondence really happens is at type checking. The process of type checking is exactly the same process you would go about proving the corresponding proposition. So when I look at a program and I say, I want to make sure this actually has type A cross B, arrow B cross A and B implies B and A, that process of checking that it has that type is, okay, well, I need to check this implication, or in other words, I need to prove this implication. Okay, well, to prove this implication, I have to check this pair. Okay, I need to prove this conjunction. And that whole step-by-step process that you would go through, even just in your head, of saying, oh, this is in fact the right program for this type, or this program does in fact have this type. That process that you would go through in your head, if you just like replace the words that you used from type to proposition and cross to and arrow to implies, it would pretty much sound like you're proving the corresponding proposition.
It did seem like he's elucidating this correspondence by saying, look, here I'm going to demonstrate how to take one of these intuitionist natural deduction proofs, and I'm going to translate it into this type of program. And you could sort of see it happen before your eyes. These really are the same thing. It's not just a correspondence. It's not even an isomorphism. You sort of said this, like you think of them as an is property. Maybe I'm overstating what you said, but I had always thought of it the same way too. Like my program is a proof. It's not, I don't care about whether it corresponds. It is if I'm working within a sufficient type system where the types themselves are propositions.
Yeah, no, exactly. That's why I really love the language Agda, because they make absolutely no distinction between the two. They're pretty much identical.
He says at the end, propositions as types informs our view of the universality of certain programming languages. And I go, ooh, universality. Wow. From a former philosophy nerd, that sounds really cool that these are universals we're talking about. But the word certain is kind of doing a lot of work here. Certain programming languages. And I kind of already asked this, but it sounds like he's probably talking simple type lambda calculus and languages that maybe are descendants from that, like what you had described, Nathan. Is that what would you sort of guess when he says certain, that's what he's talking about? Or does he mean Java and put everything in the bucket? Put C in there too. Who knows what they're doing?
No, I have to imagine that's roughly what he's saying. I co-taught a PL course this last semester with a new professor at BU named Ankush Das, and he has this joke that what we teach here is we teach you about good programming languages, and we don't tell you at all about bad programming languages like Python. So I think that it's probably roughly the same kind of distinction here. What he means by certain programs is what Ankush would refer to as a good programming language, i.e. something which has a strong type system and has a well-defined semantics and well-defined syntax.
My gut reaction to that as a software engineer who's worked with Python for 10 years is, but Nathan, you haven't seen my Python programs. Mine are pretty good.
Yeah, and this is where he would put his head down and shake his head, and you're like, damn, what have we been teaching people? No, it's a little bit of a bit in the course, but it's a fun one. I mean, obviously, I personally have no issue with any of the languages, but
so let me ask a dumb question following on to that. So the program that he provides, in Lambda calculus that corresponds to the proof, as Erik was saying, you can think of the type as being a tuple B, comma A. And producing a tuple A, comma B. So, suppose that you wrote a Python program that takes a tuple, which is an int and a string, and it outputs a tuple, which is a string and an int. Does that not count as a proof because there's no type system in Python?
Oh no, I love that question because it's. I could ask the same thing. If I write a proof and no one reads it, is it a proof? Like if I prove some mathematical theorem and I just never showed my proof to someone, is it a proof? The point is it is, but the real thrust of the propositions as types is that process of checking a proof, I don't need to have anyone read it. I can just use my type checker. So if you had an extension, or you use the extension for Python that allowed you to put type annotations, and you annotated it with a type, then that checking process is exactly checking that the proof that you wrote is correct. So, I mean, you could write the same exact program in Python, and if you wanted to, you could say, "Ah, yes, this is a proof." But then you would have to have someone look at it and say, "Yes, that does in fact prove what you claim it to be proving." But the great power is, okay, well, now I don't need to have anyone read my proof. I can just have my type checker type check it, and then hey, I know it's correct now.
I wonder if there's a space for the typical kind of rehashed, you've heard these, people have heard these conversations over and over again, but the kind of typical arguments about static typing versus dynamic typing that you get in our field. And lurking within that conversation, you have people saying, I mean, even Lamport is saying, you have to do so much work to produce a fancy type that says my division doesn't allow for zero. I don't want to divide by zero. So I need a type that can express that. And he was kind of complaining, I'd rather not even deal with types. And you have people saying, well, the problems that appear in my programs are often not typed problems. They're problems from interpreting my real world constraints, or maybe I'm looping forever, or maybe my input values are so large that my program's not efficient enough to produce. And typing is not the way out of these things. And maybe what's ultimately going on there is that people are talking about, well, you can't solve the halting problem. Maybe they're not saying that, but you know what I mean? Like there are these things that types get us. And sure, the types may be proofs if I can write programs that are well typed in a satisfying type system. Wadler's celebrating the correspondence.
No, it's fair. It's fair. I should probably add the disclaimer that as a type theorist, it is my moral obligation to convince everyone to use statically typed languages. But I do recognize that in reality, that's not the way that we should approach programming. I understand the Lamport stance, and yes, I mean, there another big issue with types is that types are they're not that robust to change. Like if you're like, oh, I actually really wanted to do this other thing, in particular with really strong type systems, that might require a massive a massive redo of all the things in your code. So this is why you get research in this notion of proof reconstruction in the world of rock and math assistants, where it's like, I made one minor change to a lemma and it broke my entire proof, but not in an interesting way, just in a way that like requires me to change little things absolutely everywhere.
Is that what Talia Ringer does?
Yeah, this is part of Talia Ringer's research is this idea like, oh, I need to change this lemma because the structure that I use to represent this thing isn't quite what I wanted to do, but that would require me to change 800 lines of code in this massive proof base that I've built up. Like, so there are real problems with the use of types, particularly for large scale projects, and like scaling up proofs is one of the big topics in the world of automated theorem proving. So yes, I do definitely understand that there are downsides, so to speak, of types as well.
I guess I was trying to give credence a little bit to those complaints and to link them to these bigger, maybe philosophical concerns that are lurking below the surface. But you say, as a type theorist, you want to urge people to use static types. But hidden in there, I do immediately go, well, don't you have a little bit of a hierarchy? Like there are some systems that are better than others. Presumably you would probably be, if you saw me writing, well, I could do C or Python, you'd probably be like, no, stick to Python, my friend. You're going to be better off. You know what I mean? Like there are probably type systems that you would say are more likely to produce effective results than others. I don't want to pin that on you, actually. Let me move on to the critiques. Here's what I want to know. Are there people in your field who are critical of this paper or the ideas that appear in it? Is that are there like common complaints, or is this just a widely accepted conclusion?
Sure. Yeah. I wouldn't say that there were any strong critiques or complaints on the idea. I think everyone recognizes that it is a beautiful idea. I think the thing that you hear the most is, okay, this is really pretty, but how is it going to help me? What do I actually want to do? And this comes back to an early complaint. I was talking to someone about, this course that I was going to teach last year on essentially these topics. And I said I was going to cover the Curry-Howard isomorphism. He's like, it's not really worth covering. And I was like, oh, why not? And his basic thought was, well, I actually do really believe that, computation is computation. Proof is proof. It's a nice analogy. It's a nice pun, as Wadler says. But at the end of the day, I want those two things to be different, because I might need different approaches in the logic side than I do in the computation side. For example, there's whole worlds where rather than trying to come up with a proof, maybe I'll use some algorithm to come up with a proof. Like maybe it's a simple enough proof that I can use what's called a SAT solver, just a general purpose logic solver, to figure out my proof, as opposed to trying to write it myself. And it's much easier to apply those tools if it's not linked directly to the programming language I'm also using for writing computations. Or like maybe another thing that you get complaints about is if I want to prove a sorting algorithm, it's much easier for me to write the sorting algorithm in a language that I'm comfortable with and then prove something about it than to embed within the program itself all of these like proof terms that are telling me that it's sorted along the way. Because if you actually try and do that, then you have to have all these intermediate structures inside of the program itself. Your program becomes a lot less readable. This is the notion of the difference between intrinsic versus extrinsic verification, whether or not the verification is happening intrinsically in the program or is something you're doing external to the program itself. So there's all sorts of those kinds of complaints. Like, it's a question of how seriously should we take this analogy, and that's maybe the basis of the debate. But at the end of the day, everyone is able to take something from the correspondence. There's some usefulness out of it. It's just whether or not you want to be a staunch a proposition is a type. Or some people even say my category is the type theory. This category is the type theory. Or if you want to just say, it's a very nice picture, and it really helps me design systems and think about the way that I should represent proofs. But that's about it. I still want to keep my two worlds separate.
I think that's similar to the critique that I heard, kind of an incidental critique. There's a guy who goes to my gym who's a computer science professor at UCSD, and his field is not programming languages. He does more systems level stuff. He does a lot of security stuff. So he's disassembling stuff. He's looking for penetration, like things he can hack. His work, I've talked to him about it. It's interesting, and he's just at my gym, so we just have these kind of incidental conversations. And I was just curious, how widespread is knowledge in computer science academia about things that Wadler talking about, proposition types? I said, "Have you ever heard of propositions as types?" He said, "Oh no, I've never heard of that." "Have you heard of the Curry-Howard correspondence?" I said. He said, "No, I've never heard it, but I'm on the same floor as the PL people, and that sounds like what they're talking about." And so he said, "So what is that?" And it falls on me to try to give a clumsy, ham-fisted description of what I know. And I said, yeah, and in the end, it's kind of like I'm a tourist for these ideas. I go in the museum, I read the signs, I look in the dioramas, and it's kind of like many years ago in Chicago, I went on the architecture tour on the river, and they go by the CBOT, the border trade, and they go, "At one time, this building was the largest uninterrupted continuous space inside a building in North America." And I go, wow, that's cool what people have built, and then I move on with my life. And I kind of wonder, is this really useful for me? Is there utility here? And he said, yes, that's exactly the question I have when I talk to these PL people. That seemed to me like he was voicing this critique, okay, that's really beautiful what you're saying. What do I get out of it? When do I get a laser that I could cut my bread with? Or when do I get something really? I'm just waiting.
Sure. Yeah. Well, just another maybe small shout out to my co-teacher from last semester, Ankush Das. He is definitely someone worth looking into if you're interested in these sorts of ideas, actually occurring in practice. He's currently working on a collaboration with another professor in our department on bringing this notion of session types into a large-scale system. So session types are types that enforce message passing protocols. So message passing protocols, obviously very important and obviously very error prone when you're writing them. So if you have a nice type system that allows you to define message passing protocols that you can check beforehand that they will be that they are sound. If you could actually have that in a large system, that would be very nice. So these ideas are making their way into actual applications, very cool applications. But I completely understand the idea that as a software engineer, it doesn't matter if your program happens to be a proof of some interesting theorem. It's a
But I mean, I find this compelling because if I had a programming language that allowed me to, again, going back to the Haskell, the Rust, like making illegal states unrepresentable, if I could really do that, if I could push the envelope on that, whatever, to the extent that my language allows, maybe it is dependent types. If that became a commonly used thing, maybe my program itself is a verification that my program is accurate. Is that contradictory? Is that like is that
no,
possible to achieve that? I want that if that exists. I want to write a correct program.
No, exactly. Yeah, I mean, whenever I talk to people who are not in computer science but not in PL, I tend to say, the way that I think about the future of types is that, types restrict the kinds of programs that you can write. Like, and if you know the things that go wrong in the kinds of programs in whatever domain that you're working in, if you can, sufficiently express what those things that you want to avoid, those things that you want to avoid, if you can sufficiently express what those things are, then you can probably write a type system that can check it. And then it would, like, you can use all of these ideas to influence how you design that program in that programming language. And you could end up with something that's really beautiful, but also very useful. And I think that's a very compelling thing, and at least in my opinion.
I want that. When can we have that? We having that soon? That's what I want.
It probably depends a lot on your view of the world too. I mean, if, like, with the session types, if your objective is to make things more correct and more safe, then that looks like a nice thing. But if your objective is to, sling more bits across this wire, then maybe that's not the key thing for you.
Can you imagine formally proving that a CSS selector really is vertically centered?
Yeah, see, it's those sorts of things where you start to question how how romantic the notion is.
Well,
yeah, I mean,
Wadler's certainly really romantic. Go ahead, Nathan. I'm sorry.
Yeah, I was just going to say, I mean, even in a slightly more serious case, I mean, there are lots of security breaches that are completely irrelevant with respect to the types. Like, you can have a completely type-safe thing, but it's not going to save you from certain security attacks. It's that's out of my reach. I'm not going to try and express which ones those are, but I've talked to security people enough to say, like, yeah, that's not really going to help you if you tell me that this is completely secure according to some type theoretic notion.
Wadler, there's a philosophical attitude that I can't help but notice as I read this paper, and that is, I mentioned it before, but mathematical Platonism, the belief that mathematical objects are maybe even belief is already talking about it as a belief, but the belief that mathematical objects, they exist outside of our brains, right? Like, they're abstract things. There might be numbers, there might be prime numbers, that those things would exist whether or not humans ever came along to dream up some imagining of them. And the properties, the rules, the ways they interact, those are outside of human knowledge, to be waiting to be discovered. That's a mathematical Platonism. I don't know. I mean, I had thought that people still argue about this in philosophy departments, but Wadler's really taking it as a given. He's saying philosophers might argue as to whether mathematical systems are, quote, discovered or devised, but the same system arising in two different contexts argues that here the correct word is discovered. So he's planting his flag. It's almost like we're going into, he's sort of like, here you are in the church of mathematics and logic and type theory, and I'm going to show you how all these things are together, and they're just being independently discovered over and over again. So I guess I wonder, too, if there are people out there who are like, these are all just funny rules that we're inventing as we go along in order to deal with other things we've already invented in the past. I don't know if that's a critique that people actually make. maybe those are people who in math and the logic and they don't care about that argument that's happening outside. The Wittgenstein, maybe, type of argument. We don't care about that one.
Yeah, I mean, honestly, I don't talk to enough philosophers to decide whether or not that is or is not a common argument that people are making.
Fair.
I don't know. But even then, I mean, regardless of whether or not you take mathematical Platonism to be your, foundations of mathematics, it certainly points to some notion of usefulness if we happen to come across the same idea over and over and over again. There must be something to it, I guess. I don't
think
know.
that's the Frege argument, is it not?
Yeah,
Isn't that the argument that Frege made? I call it, yeah. Hey, this is super useful, so good enough, okay?
Yeah.
All right, how'd we do? Is there any other thing that we should come back to? Did we skip anything? Did we need to clarify, correct, or... I also am really bad at ending these, Nathan. We get
No,
to the
that's
end
fair.
and I'm like, okay, I don't know what to say to finish this off.
No, it's fair. I've also jumped in a billion times here, so I never know how to end my own thoughts.
I think there's some really good stuff that you provided to help us understand what's going on in here.
Yeah, I mean, I love talking about this stuff, so I definitely have no issue with that.
One thing I would say that you said that was interesting, and I didn't really appreciate this, I guess. But you said without propositions as types, we wouldn't have Rust. And that's kind of a pretty solid argument for the utility of these ideas, I think, right?
Yeah, I'd like to believe so. I mean, at the end of the day, I'm sure at this point we would have some language which is enforcing some notion of memory safety. That's something that people care about enough to try and implement. But I think the idea that this was already an idea that people thought, oh, this could be useful. And just the fact that all we have to do is translate this notion into programming languages. I think that's the thing that makes Rust as well designed as it is. Not to say that Rust is completely well designed, but it wasn't a matter of starting from the ground up. There's this whole existing framework to be thinking about these ideas. And as we get further into developing Rust, there will be things that will influence logic and vice versa. It's this whole back and forth between these two interpretations as a program or as a proof and as a type and as a theorem. Jumping between those two interpretations just feels like a really fun place to be, to design and develop new programming languages. And even as we were talking about this, I was like, I haven't actually seen a programming language that uses counterfactuals. Maybe there's something interesting there. I'm sure someone has thought about it, but like a Curry-Howard correspondence for counterfactual logic. Like, it's just, you can start playing this game of, okay, there's a weird logic I've seen before, some bizarre what am I thinking? Bizarre modal logic, some kind of strange thing that I've spent a lot of time thinking about for some bizarre reason. It's like, oh, well, maybe I should try and turn that into a programming language. Or like, oh, I have this weird programming pattern that keeps coming up over and over and over and over again. Maybe it has some underlying logical structure. It's like, I guess it's just the fact that because in essence, all we're doing when we program is applied algebra, that things fit together very nicely, and this gives us the framework for seeing how those things fit together really nicely, and the language for talking about those things.
Well, and for me, sitting in the audience, looking up at the movie screen, there's a hint in what you're saying. In just over the horizon might be Rust with dependent types, and it's a new language, and it's going to allow you to express even more correct programs. There's like this grasping, this reaching. There's something coming in the future if people keep banging these ideas together. That's the hint of it.
Yeah, absolutely. And yeah, I guess the one disclaimer on that, I've fulfilled my moral obligation to tell you how cool types are. The other moral obligation is that if people actually care to like learn more about types, the one thing about types is that they are not robust to change. And that even comes in the theory side. So like the idea of, for example, putting dependent types in Haskell has been an idea for nearly a decade now. And my understanding is that the people who were originally pushing that have since dropped that desire for a number of reasons, one of which being that it's nearly impossible to recover type inference if you have dependent types, which is something that Haskellers really care about. Like if you lose type inference, you lose the ability to do a lot of concise Haskell coding. So it's like these meta-theoretic properties, you're like, okay, now I get to add dependent types to Rust and see what happens. Well, be prepared for a lot of things to break. Like things will fall apart very quickly in ways that you don't even necessarily expect. Even languages like Agda, or like let's try putting in this new feature. And then 2 weeks later, someone's like, oh, actually, that makes the entire system inconsistent. We can't do that. It's fascinating to me just how not immediately obvious the issues that you're going to run into are once you start trying to extend your type system. And people are working on this problem. There's lots of nice ideas of like compositional type theories where you can like link things together nicely. So like have this and then link together this new feature without losing too much. There's this notion of like gluing where you can like glue together two type theories. But the point being that, oh yes, it's very exciting to imagine Rust with dependent types, but that might be a much farther horizon than you might imagine at the moment is all I'm saying.
Nathan, I'm sitting here waiting. Okay, it's been done yet.
No, I mean, I'm right there with you.
Well, I assume that the super intelligent AIs will solve it for us, and as I understand it, that's like 2027 or so.
Oh, I've been reading about Gödel and Penrose, and this is not going to help us, but that sounds like something Penrose would be like, no, not going to happen. Right?
Yeah, we'll have to see if he wants to be a guest on the podcast.
That'd be great.
Well, this has been amazing. Thank you so much, Nathan, for your help. Unpacking, understanding propositions types. If people want to know more about your work, is there somewhere they can go to find out more about the work that you're doing?
Sure. Well, I have a website, and that's where I keep most of my things. Yeah, I don't know. Do you have links and
we can
show notes or anything?
Well,
I can just throw it in the show notes. That'll be easiest.
Okay. Yeah, that'd be great. Thanks so much for joining us today, Nathan Mull.
Oh, thanks for having me.
This has been Picture Me Coding with Erik Aker and Mike Mull, and we'll see you again next week.
See you next time.